Hello and welcome to this online lecture. My name is Patty Kokish and I teach Math 200 in the Northwest region. Today we're going to be going through week 13 topics for your stats class. We're actually backtracking a bit and we're going back and covering chapter 4, which is all about describing the relationship between two variables. So we're going to start with section 4.1, which is about scatter diagrams and correlation. The objectives are to be able to draw and interpret scatter diagrams, describe the properties of the linear correlation coefficient, compute and interpret the linear correlation coefficient, determine whether a linear relation exists between two variables, and explain the difference between correlation and causation. So objective 1 is to be able to draw and interpret scatter diagrams. First, we need to know a couple of things. The first is that the response variable is the variable whose value can be explained by the value of an explanatory or a predictor variable. A scatter diagram is a graph that shows the relationship between the two quantitative variables measured on the same individual. Each individual in the dataset is represented by one point on the scatter diagram. The explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. So the data shown to the right are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable, which is x, and time in minutes to drill 5 feet is the response variable, which is y. So the first thing that we want to do is draw a scatter diagram of this data. So you'll see we have, a few different things here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different pairs. We have an x value, which gives us our depth at which the drilling begins in feet, and then the time to drill in minutes. And what we see is if we plot our depth on the x-axis and the time on the y-axis, time is between 6 and 8 minutes, depth is between 50 and 200 feet, we see that each dot represents one of our ordered pairs. So we want to talk about the various types of relations that a scatter diagram can show. So if we look at this very first one, this is A, if we have our explanatory versus our response variable and we get something that looks like this is a linear relationship because all of our points are lying on approximately a line. They're never going to be perfect, but this looks pretty linear if you take a look at it. The same is true with B, okay, but that one's decreasing. We're going to talk about the difference between these two things in a little bit. If we look at C, we have sort of this U shape. This is a nonlinear relationship. So there's clearly some kind of relationship going on, but it's not a line. So we're not going to be dealing with it in this class. The same is true with D, okay? This also looks like there's some kind of relationship between the two because we see a pattern, but it's definitely not linear. And then if we look at E, this kind of just looks random, okay? So there's no relationship between these two. So we would just say no relation. So two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of another variable. And below average values of one variable are associated with below average values of the other variable. That is, that two variables are positively associated if whenever the value of one variable increases, the value of the other variable also increases. Negatively associated is just the opposite. So when we have above average values of one variable, that would be associated with below average values of another, meaning that the two variables are negatively associated if whenever the value of one variable increases, the other one decreases. So if we go back for just a second, you'll see that this first one, this is a positive relationship. We have a positive slope. This one would be a negative relationship. Objective 2 is to describe the properties of the linear correlation coefficient. So the linear correlation coefficient, or the Pearson product moment correlation coefficient, that's another name, is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and R represents the sample correlation coefficient. We're only going to look at the sample correlation coefficient formula. So we have this formula here. Thankfully, you can normally use some kind of technology to help you do this. We typically wouldn't do this by hand. We'll show you how to do that, but typically you could use a graphing calculator or a product like Minitab or Excel to help you do this. So we have our formula here. Our sample linear correlation coefficient, that's R, is going to be equal to the sum of this entire numerator. So we take our xi minus our x bar, divide by sx, and multiply that by yi minus y bar over sy, and then divide that whole thing once you've added it all up by n minus 1. So let's talk through all of these pieces so you guys make sure you remember what all of this stuff is. X bar is the sample mean of the explanatory variable. S of x is the sample standard deviation for the explanatory variable. Y bar is the sample mean of the response. S of y is the sample standard deviation of the response, and n is the number of individuals in the sample. So there are some important properties of the linear correlation coefficient. The first is that it is always going to be between -1 and 1 inclusive. So we could also write that as -1 is less than or equal to r, which is less than or equal to 1. So you can never have a correlation coefficient that's smaller than -1 or larger than +1. If r is equal to +1, then we have a perfect positive linear relationship between two variables. If r is equal to -1, then we have a perfect negative linear relationship between two variables. The closer that r is to +1, the stronger the evidence of a positive association between the two. The closer that r is to -1, the stronger the evidence of a negative association between the two. If r is close to 0, then we have little or no evidence to suggest that there is a linear relationship between the two variables. So r close to 0 doesn't imply that there's no relation, just no linear relation. So there could be some kind of quadratic or maybe cubic relationship between the two, logarithmic, exponential, something, but it just implies that there is no linear relation. The linear correlation coefficient is a unitless measure of association. So the unit measure for x and y doesn't play any interpretation or any role in the interpretation of our r. And the correlation coefficient is not resistant. So therefore, if an observation that doesn't follow the overall pattern of the data exists in your data, then it could affect the value of your linear correlation coefficient. Okay, so we're going to look at a couple of different situations here. If you look at A, we have a completely straight line. This is a perfect positive linear relation because we have a positive slope. So that would be a value of r equals 1. If we look at B here, this is very linear still, okay? It's what we would maybe call a strong positive linear relation. So we definitely have something that's positive and linear, but it's not exact, so it's not gonna be 1. That would maybe be something like R is around 0.9, something like that. If we look at C, that's a moderate positive linear relation. So there's definitely still some kind of linear relationship, and it's definitely positive, but it's not nearly as strong as some of these others. So that's an example where R is maybe somewhere around 0.4. If we look at D, this looks a lot like A, but just kind of flipped around. This is a perfect negative linear relation. So that would mean that R is -1. In E, we have a strong negative linear relation, so we definitely have a negative relationship that's linear, but it's not perfect like D was. So that's an R that's somewhere around -0.9. If we look at F, that would be an example of a moderate negative linear relationship. So it's definitely linear, definitely negative, but not nearly as strong as D and E. So that would be something around R equals -0.4. If we look at G, these all kind of look random. There doesn't appear to be any real relationship here. So R would be close to 0, and there's definitely no linear relation. If we look at H, there's some kind of relationship between the two. Okay, this looks like a quadratic, but it's not linear. Okay, so that's going to also yield something where R, our linear correlation coefficient, is close to 0. All right, so in order to compute and interpret the linear correlation coefficient, we have to have some data. So we take our x's and our y's, and we want to set up a table. Now, there's really no reason to not do this in Minitab, Excel, or some other type of statistical tool, maybe your calculator even. But if you want to do this by hand, what you do is you take your xi minus your x bar, and the first thing you would have to do is you'd have to calculate x bar and s of x, okay, to get what your sample mean is for your depth and your sample standard deviation, and then you'd have to do the same thing for y's. So for this very first value, I'm not going to walk you through all of these, but to get the very first one, you'd take your 35, you'd subtract your 126.25, and then you divide by the standard deviation of 52.22874, and you would get negative 1.74712. To get this next column, you do the same thing but with y's. So you take your yi, which is your observation that you're talking about, so this 5.88. You subtract your y bar, which in our case is 6.985833, and then we divide that by the sample standard deviation for our y's, which is 0.780774, and we get negative 1.41633. And then what you do is you multiply these two things together. Okay, so that's this last column here, and we get 2.474501. And we do this all the way down, okay? And then what you need to do is you need to take this entire column and add it up, and we get 8.50137. And once we have that, we have to divide by n minus 1, which in our case we had 12 observations, so we divide that by 11, and we get 0.773. It's important to always note that you need to make sure that you calculated something that is between -1 and 1. If it's not between -1 and 1, then you made some kind of mathematical error in your calculation. Okay, objective 4 is to determine whether a linear relation exists between two variables. So if we want to test for a linear relation, step 1 is to determine the absolute value of the correlation coefficient. Find the critical value in Table 2 from Appendix A for the given sample size. And then if the absolute value of the correlation coefficient is greater than the critical value, we say that a linear relation exists between the variables. But if that's not the case, then we would say that no linear relationship exists. So we have our same problem here. We found that the correlation between drilling depth and time is 0.773. That was the calculation that we did a couple of slides ago. If we look up our critical value for n equals 12, it's going to be 0.576. Since we know that 0.773 is larger than 0.576, we can say that there is a positive linear relationship between the time to drill 5 feet and the depth at which the drilling begins. Okay, objective 5 is to explain the difference between correlation and causation. So according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. So we want to know, does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? And certainly it does not. The correlation exists only because both percentages have been increasing since 1990. It is this relation that causes the high correlation. In general, if we're talking about time series data, which is data that's collected over some period of time, you might have high correlations just because both variables are moving in some kind of specific direction over time. So either both are going up, both are going down, one is increasing while the other is decreasing. But when data is observational, we cannot claim that a causal relationship exists between two variables. We can only claim causality when the data is collected through some kind of a designed experiment. Another way that two variables can be related, even though there is not a causal relationship, is through a lurking variable. So a lurking variable is some variable that is related to the explanatory and the response variables that you may not have thought of. So for example, this is a really typical example. Ice cream sales and crime rates have a really high correlation, but we want to know if that means that local governments should shut down all ice cream shops. Well, no. If you think about what kind of relationship ice cream sales and crime rates would have, you might think that as our temperature increases, ice cream sales are obviously going to increase, and crime rates also increase in the summer months. So it makes sense that they're highly correlated, but it doesn't mean that one causes the other. Okay, Because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers Catherine L. Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. So cohort study is where we follow someone over time. So we have number of colas here, and then bone mineral density in grams per centimeter squared. So the figure on the next slide shows the scatter diagram of the data. The correlation between the number of colas per week and bone mineral density is negative 0.806. The critical value for correlation with n equals 15 from our second table in that Appendix A is 0.514. Since the absolute value of negative 0.806 is larger than 0.514, we can conclude that there is a negative linear relationship between the number of colas consumed and bone mineral density. But what we want to know is, can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? And you can see, here's the scatter diagram. So in prospective cohort studies, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So the researchers cannot claim that the increased cola consumption causes a decrease in bone mineral density. Some lurking variables could possibly be body mass index, height, smoking, alcohol consumption, calcium intake, physical activity. I'm sure there are others that aren't listed here that are also fine. There are a million possible lurking variables in a lot of different situations. So the authors were careful to say that increased cola consumption is associated with lower bone mineral density because of potential lurking variables. They never stated that increased cola consumption causes lower bone mineral density. So they can say that they're associated, but not that they have a causal relationship. Okay. Section 4.2 is about the least squares regression line. So the objectives are to actually be able to find the least squares regression line and use it to make predictions, interpret the slope and the y-intercept, and then compute the sum of squared residuals, which is what I just went through. Sorry, 2 duplicate slides there. Okay, so here's our first example. It's for finding an equation that describes linearly related data. So if we have the following data, this one we don't have a scenario around, but we have just x, y pairs. If we want to find a linear relationship, a linear equation that relates x, which is our explanatory variable, with y, the response variable, by selecting 2 points and finding the equation of the line. So we can just pick any 2 points that we wanted, but in this case, we've chosen 2 and the 5.7 and the 6 and the 1.9. Hopefully you remember how to calculate slope. We take our 5.7 minus our 1.9 and divide it by 2 minus 6, and we get negative 0.95, which would be our slope. And then we just pick one of those points that we just used. In our case, we're going to pick the 2 and the 5.7, and we plug it in to this equation right here. This is your point slope form for your equation of a line. Y minus y1 equals m times x minus x1. So we do y minus 5.7 equals our slope, which we just calculated to be negative 0.95, times the quantity x minus 2. We distribute our negative 0.95 and add 5.7, and we're left with y equals negative 0.95x plus 7.6. And then here we have a scatter diagram and also the equation of the line that we just drew. So if we want to use our equation to predict y if x is 3, all we have to do is just take x equals 3 and plug that into our equation. So we let x equal 3, plug it in, and we get 4.75 as our prediction. So that can be useful, but depending on which points we picked, we could have ended up with a lot of different lines. We could have picked any of these pairs. So what we want to do is we want to come up with a more sophisticated way of creating a line that makes the best predictions possible. So we want to actually find something called the least squares regression line, and then we're going to use that line in order to make hopefully pretty good predictions. So the difference between the observed value of y and the predicted value of y is called the error or the residual. So using the line from the last example and the predicted value of x equals 3, what we do is we say that the residual is our observed y, which was 5.2, minus our predicted y, which we calculated to be 4.75. So we got 0.45 for that residual. So you'll see here it is on the graph as well. So the least squares regression criterion, basically the least squares regression line is a line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distance between the observed values of y, and those are predicted by the line of y, sorry, this should be y hat. We represent this as minimizing the sum of the squared residuals. So the least squares regression line is going to look something like this. Y hat is going to be equal to b1 times x plus b0, or b naught. b1 we're going to calculate as r, which is our linear correlation coefficient, multiplied by the standard deviation for our y's over the standard deviation of our x's. That gives us the slope of our least squares regression line. We always have to calculate that first, because then we use it in order to calculate b naught, or b0. So b0 is going to be calculated by taking y bar minus b1, which we just obtained, multiplied by x bar. And that gives us our y-intercept for our least squares regression line. Okay, so it's important to note x bar is the sample mean and s of x is the sample standard deviation of the explanatory variable x, y bar is the sample mean, and s of y is the sample standard deviation of the response variable y. Okay, so we're going to use that same drilling data. We're going to find the least squares regression line, make a prediction, determine if the observed drilling time at 130 feet above is above or below average, and then draw the least squares regression line on a scatter diagram. So we agreed to round the estimates of our slope and our y-intercept to 4 decimal places. So we have y hat equals 0.0116 times x plus 5.5273. And this can be done just using any kind of statistical tool, your calculator. The book walks you through how to do that. You can use Minitab, Excel, lots of different options. And then if we want to make a prediction at 130 feet, we just set that equal to our x value, and we get a y hat of 7.035. The observed drilling time is 6.93 seconds. The predicted drilling time is 7.035. So the drilling time of 6.93 seconds is actually below average. So here we have our scatter diagram. It might be kind of hard to see, but we do have these blue dots here. And then we have our black regression line, which was what was just created. Now we want to be able to interpret the slope and the y-intercept. So the interpretation of the slope, you have to think a little bit when you're doing these, but the slope of the regression line is 0.0116. So for each additional foot of depth that we start drilling, the time to drill 5 feet increases by 0.0116 minutes on average. So you always kind of want to think about it. If you increase x by 1, what's happening to y? And then you want to form a sentence using the actual scenario that you were given. Now, interpretation of the y-intercept. So the y-intercept of our regression is 5.5273. To interpret it, we have to first ask a couple of questions. Is 0 a reasonable value for our explanatory variable? And then 2, do any observations near x equals 0 exist in the data? So a value of 0 is reasonable for the drilling data. That would mean that we're starting to drill at the Earth's surface. The smallest observation for the data is x equals 35 feet, which we could say is reasonably close to 0. So it is okay to be able to interpret the y-intercept in this case. In some cases, you're going to get y-intercepts where it just doesn't make any sense to interpret. But here we would say that the time to drill 5 feet when we begin drilling at the surface of the Earth is 5.5273 minutes. Okay, so here is kind of a cautionary message. If the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we see the researcher is working outside of the scope of the model. So we never want to use the least squares regression line to make predictions outside of the scope, because we can't be sure that the linear relationship continues to exist. So we've built it for a certain set of data, and we can't extrapolate that to really large or really small values that don't exist in our data already. Okay, objective 3 is to compute the sum of squared residuals. So to illustrate the fact that the sum of squared residuals for a least squares regression line is less than the sum of squared residuals for any other line, you can use something called the regression by eye applet, and that exists on your stat lab that you have associated with my math lab. Okay, section 4.3 is all about the coefficient of determination. So objective 1 is to compute and interpret the coefficient of determination. So the coefficient of determination is normally denoted with r squared. It measures the proportion of total variation in the response variable that is explained by the least squares regression line. The coefficient of determination is a number between 0 and 1 inclusive. That is to say that 0 is less than or equal to r squared, which is less than or equal to 1. If r squared is equal to 0, the line has no explanatory value. So it's not a coincidence that we had kind of the same statement being made when r is 0. The two are related, and we'll talk about that in just a minute. And if r squared equals 1, that means that the line explains 100% of the variation in the response variable. So if you recall, when we had little r, our linear correlation coefficient, equal to 1 or negative 1, that meant we had a perfect linear positive or negative relationship. So when we square that, we get r squared equals positive 1. This is capital R squared, our coefficient of determination. And that would mean that we're explaining all of the variation in the response variable using our line. Okay, so we're going to go back to our data on the study for drilling rock. The researchers, just to remind you, did want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which their drilling begins. So the depth at which the drilling begins, that was our x variable, and then the time in minutes to drill 5 feet is our y variable. So we had these 12 observations. And we looked at a scatter diagram. You can see that there's probably some kind of positive relationship between the two because we do have kind of this trend here. It's not perfect by any means, but it's not too bad. So we do have some sample statistics. These would be calculated either using Excel, Minitab, your graphing calculator, and the mean and the standard deviation were calculated for each. So the mean for the depth was 126.2. The standard deviation for the depth was 52.2. The time was 6.99 for the mean and 0.781 for the standard deviation. So the correlation between depth and time, we already had calculated that. That was 0.773. And then using our regression analysis, we came up with an equation of time equals 5.53 plus 0.0116 times our depth. 0.0116, that was our slope. 5.53 was our y-intercept. So let's suppose that we were asked to predict the time to drill an additional 5 feet, but we didn't know the current depth of the drill. So what would be our best guess? So if you think about it, the mean time to drill an additional 5 feet is going to be 6.99 minutes. So that would be kind of the best guess, would just be to guess the average, all right? So it's not going to be perfect, but it's not a bad guess either. Okay, now suppose that we are asked to predict the time to drill an additional 5 feet if the current depth is 160 feet. So in order to do that, it would be best to actually use the equation that we created. So we have that equation, y hat equals 0.0116 times x plus 5.53. So all we have to do is just plug 160 in for x. So if we were interested in 110 feet or 150 feet instead, we would plug those numbers in for x. But since we were interested in 160 feet, that's our x value. So if we plug that into our calculator, you're going to do 0.0116 times 160, hit enter, and then add 5.53, and you get 7.39. So our guess has increased from 6.99 minutes to 7.39 minutes based on the knowledge that drill depth is positively associated with drill time. So we would notice that as we put smaller values in, like if we had 80 feet or 50 feet or 10 feet, our values would get smaller and smaller, the smaller value that we put in for x. Okay, so here's our regression plot here. So I want to point out a couple of things. First is that depth is our x value, so it's along our x-axis. Time is our y value, so it's along the vertical y-axis. We have times between 6 and 8, and depths between 50 and 200. Well, it looks like there's a value, I think it's a little smaller over here. The black dots that you see, there should be 12 of them. Those represent each of our actual data points that we found. And I think this particular graph was created in Minitab because what you'll see is we have our regression equation right here, and we're given an R squared value of 59.7%. So this was already done for us. So if we look from our line to this point, that's the difference that's unexplained by the drill depth. And then if we look from our average line, so if you look at this red line here, y bar equals 6.986. If we don't know what depth we're talking about, we're just always going to guess whatever the average would be, which would be 6.986. But it's not a very good guess. I mean, it's an okay guess for a couple of observations, but most of them are really, really far away from this line. So if you look from the red line up to our black prediction line, that's the difference that is explained by drill depth. So you'll see that there is difference that we cannot explain, that's the unexplained, but we also have differences that we do a pretty good job of explaining. So the difference between the observed value of the response variable and the mean value of the response variable is called the total deviation. And the total deviation is going to be equal to y minus our y bar. Now, the difference between the predicted value of the response variable and the mean value of the response variable is called the explained deviation. So that's the part that we do have the ability to explain. And that's going to be equal to our y hat, which is our prediction made by our line, minus our y bar. Now, the difference between the observed value and the response variable and the predicted value and the response variable is called our unexplained deviation. And in order to get unexplained deviation, we just take our y and we subtract our y hat, which is our prediction. So we're taking whatever observation we're looking at and we're subtracting our prediction. So if we look back here for a second, if you look at your unexplained, we have our actual y value and then we have our predicted value. This difference between these two is what's unexplained. But then if we take our y hat value and our y bar value, which was our average, and we look at this is the difference that was explained by drill depth. So let me skip back to where we were. And here's another picture that doesn't pertain to the data that we were looking at, but just kind of generalizes it. We have our y bar and we have our x bar. So if you look, this is y bar, here's our x bar. So the total deviation is going to be the sum of these two things. And if we look on our line, that's our y hat, okay? The equation is for y hat is going to be b1 times x plus b naught, or b0. So the unexplained deviation exists from our actual point to where our predicted value is, but the explained deviation, which is what we have the ability to actually control and what we're good at, is basically from your y bar to your y hat value. And then the total deviation, which I pointed out was this right here, that's going to be the sum of your unexplained and your explained deviation. So we know that total variation is unexplained variation plus explained variation. So if we kind of rearrange these in some interesting ways, what we can say is that if we divide everything by total variation, we get 1. Okay, so if we divide everything by total variation, we have 1 equals our unexplained variation over our total variation plus our explained variation over our total variation. Now R squared, that's kind of telling us how good of a job did we do. That's going to be our explained variation over our total variation. And in order to get that, if we just subtract our unexplained variation from both sides, then we have explained variation over total by itself. So R squared is really just 1 minus the unexplained variation over our total. So to determine R squared for the linear regression model, you simply square the value of the linear correlation coefficient. So remember when we calculated the little r, all you have to do is just calculate the square of that. So you just take that number squared and that gives you your R squared value. Now, there's a little caution note here. Squaring the linear correlation coefficient to obtain the coefficient of determination only works for the least squares regression model. It does not work in general for other methods. Okay, so let's find and interpret the coefficient of determination for our drilling data. So we know that the linear correlation coefficient, that was our little r, is 0.773. So if you would like to figure out r squared, all you have to do is take your 0.773 and you square it, and you end up with a smaller number, 0.5975. You should always get a positive value for r squared, because whenever you take a number and you square it, if it's negative, it's going to become positive. If it's positive, it's going to stay positive. So you get 0.5975. Now, it's pretty common. You normally want to write this as a percentage, okay, because that's going to help in our interpretation. So it's 59.75%. So what we can say is that 59.75% of the variability in drilling time is explained by the least squares regression line. So you want to make sure you're comfortable with being able to select what the interpretation would be. You can always write a sentence like this, though, where you have blank percent of the variability in whatever your variable is explained by the least squares regression line. Okay, so we want to draw a scatter diagram for the data. For data sets A, B, and C, we have 3 different sets here, just X's and Y's. And then it tells us that for each data set, the variance of Y is 17.49. So if we look at data set A, what you'll see is we have all of these black dots. Those are that's our scatter diagram. And then we probably use some kind of software like Excel or Minitab to create these regression lines. So for data set A, we ended up with a regression line of 1.2992 times X plus 4.2159. Now for data set B, we have something that looks pretty similar, except you'll notice our dots are not in as quite of a straight line as our data set A. So we did go ahead and come up with what looks like a pretty good least squares regression line. Y hat equals 1.1797x plus 4.8438. And then data set C, what you'll see is we might have some kind of relationship between the two, but it really looks pretty random, and our line does not look great. We have several observations that are really far from our line. So we end up with a y hat equals 0.4368 times x plus 8.1464. And what we want to do is we want to compare these 3 in terms of what their r squared values are, so that you can see kind of visually what r squared actually means. So if we look at data set A, if you calculate the r squared value, which you would have to know what r is first, but you get 0.9999. And if you change that into a percentage, you get 99.99%. So in order to interpret that, we would say that 99.99% of the variability in y is explained by the least squares regression line. So for data set B, what you'll notice is our r squared value went down a little bit. It's still pretty high, 94.7. That's a really good r squared value. So we would say that 94.7% of the variability in y is explained by our least squares regression line. But for data set C, we already kind of pointed out this line is not very good at predicting our data. We have many data points that are really far from our blue line there. And this one, the r squared value is much, much smaller. It's 9.4% or 0.094. So we can say that 9.4% of the variability in y is explained by the least squares regression line. So that is it for this week. I don't think there's anyone logged on, so I'm not going to take time for questions.